Continuing with our theme of packet switching, in this video I'm going to tell you about some useful properties of queues. These are going to come in handy whenever we're thinking about how a queue evolves, how a packet buffer changes to affect the queuing delay of packets through a network. As we've seen before, we can think of a network as a set of queues interconnected by some links. And those links are carrying the traffic or the packets from many, many different users. And when multiplexed together, when statistically multiplexed together, that whole process of packet arrivals is very, very complicated. So we usually think of the arrival processes as being random events. Each one was of course deterministically generated, but the aggregate we can think of as a random process. So it's going to be good for us to understand how queues with random arrival processes work. And so that's going to be the topic that I'm going to be discussing today. So usually arrival processes are complicated in systems like networks, so we often model them using random processes. And this study of queues with random arrival processes is called queuing theory. And queuing theory you've probably heard of before has a reputation for having very hairy mathematics. But despite that hairy mathematics, queues with random arrival processes have some really interesting properties that's going to be good for us to understand. They're going to really help us understand the dynamics of networks. So I'm going to go through a set of properties. I'm going to be starting with this one here, that the burstiness tends to increase delay. And it's at this level that I want you to remember these properties. The details, the mathematics, we're not going to worry about so much. I want to understand these basic intuitive properties of queuing systems. So it all comes down to the way that the queue evolves. So I'm going to just sketch here my queue again. This is the arrivals to the queue of our packets. You'll hear people call customers as well, because queuing theory applies to many other systems. So if I say customers, I mean packets in this context. And so this is our arrivals, these are our departures. And we're going to be thinking about the evolution of the queue occupancy, Q of t, Q as a function of time. On this timeline down here, I've drawn a sequence of arrivals and departures. Packet arrivals happening at these blue downward arrows representing the time or the epoch of the arrival, and then these red upward arrows being the departures, the times at which the queue was serviced. And just like in many queues for networks, we're going to think of this as representing a link of a fixed rate R, which means that the inter-departure opportunities are at 1 over R apart. Now let's look at the evolution of the queue. The queue here has there's the first arrival, the blue one, which takes it up to 1, and then we have the service, the upward red arrow, which is going to take us to 0. There's a new arrival, which is going to take us back to 1 again. Then there's this departure here, which is going to take us to 0, then back up to 1 again, then 0, etc. At this point here, we've had 2 arrivals in a row, which is going to take us back to a queue occupancy of 2, and so on. So this is going to be the evolution of the queue. Now let's look at this one here, this departure opportunity. The reason I've drawn this as a dotted line, this is sometimes people call this a shadow departure. It was a departure opportunity when we could have sent a packet, but the queue was empty, so that we never actually sent the packet, because we can't actually go down to a negative queue occupancy. That wouldn't be possible. And so the queue sticks at 0 even though we missed this opportunity. It's going to turn out that these missed opportunities are quite important. You can't have a negative queue occupancy, so some people say you don't get credit for good behavior. By not having an arrival during this interval here, it meant that the queue occupancy stuck at 0, but we don't get any credit for it. And so if we have random arrivals with arrivals that are spread out, if we miss an opportunity to send, it's tough. We never get that back again. Let's now take a look at the first property I wanted to explain, and that is that burstiness or bursty arrivals tend to increase delay. I'm going to start with a very simple example where there is no burstiness, where we have the simplest arrival process, which is a sequence of arrivals all exactly 1 second apart. So this is 1 packet per second, and in fact it's 1 packet exactly every second. Nothing random about this at all. Let's look at the sequence of departures. I'm going to assume that there is 1 departure every second. So if we were to sketch the queue occupancy here, I won't sketch the graph, I'll just put the numbers in. If we were to sample the occupancy here, there'd been an arrival but no departure, so we'd have 1, and then 0, and then it's 1 again, and then 0, 1, 0. So these long, in this the way I've drawn it here, there are long periods of 0, and then these short periods of 1 when there's been arrival but no departure. But of course I could shift either the arrivals or departures and make those zeros and ones be of different durations. Okay, so they'll just carry on because everything's nice and periodic. The interesting thing to note here is Q of t, the Q occupancy, is either 0 or 1. So we can say it's always less than or equal to 1. And the average Q occupancy is going to be somewhere between 0 and 1. We know that for sure, just because of the structure of the problem. So periodic arrivals make for a nice, simple understanding of that Q evolution. Now let's look at a different example when things are more bursty. So just as before, the arrivals are going to be at the rate of 1 per second, but they're going to arrive in bursts. And in fact, we're going to have n arrivals. We're going to have n arrivals every n seconds. So n packets every n seconds, but they're going to come in these bursts of n. In this particular case, it's 5 packets every 5 seconds. The service opportunities, or the departures, are going to be the same as before. We're going to have 1 per second. So in terms of the rates, the arrival rate and the departure rate, everything is exactly the same as before. It's 1 packet per second. It's just that the burstiness of the arrivals is going to change things, and let's look at the way in which they change. So here we've got a sudden burst of arrivals of 5. So depending on when we sample the Q occupancy, we're going to have Q of t equals 0 all the way through to 5, depending on when we sample. During this time here, it's 4, then 3, then 2, then 1, then 0, and then it's going to go up to 5 again sometime in here, and 4, and so on, and so on, and so on. Okay? So before, our Q occupancy was 0 or 1, but now, even with the same arrival rate and even with the same departure rate, our Q occupancy can go between 0 and 5. So our average Q occupancy is higher. And the variance of the Q occupancy is higher too, because it's varying all the way across 0 to 5. So average and the variance have both increased, even though the rate hasn't changed. So clearly the burstiness is going to make a big difference. And in general, we say burstiness increases delay. And that simple example, it illustrates it. It doesn't prove it, but hopefully it gives you intuition as to why burstiness will increase delay. The second property, which is very similar to the first, it's almost the counterbalance of the first, is that determinism tends to minimize delay. But it's enough for us to know that, in general, determinism minimizes delay. In other words, random arrivals wait longer on average than simple periodic arrivals. Okay, let me move on to the third property I'd like you to know about, and that is a well-known result called Little's result. Q's are very complicated, and as I've already given you an indication, the mathematics tends to get very hairy. But there are some simple results that you really need to know, and it's important for us to understand, because they're going to come in handy when we're understanding the basic properties of Q's. And this one, Little's result, is deceptively simple. So in any queuing system like the one shown here, there's a following property which is a little surprising. If I've got a well-defined arrival rate, let's call that lambda, and I've got an average number of queues in the system, L, and I want to know what the average delay is, and I'm going to call this D equals average delay of a customer or a packet through the queue. Then Little's result tells us that there is, in general, the number of customers in the system equals the average arrival rate times the average delay of a customer through the queue. That's it. This deceptively simple result applies for any queuing system for which there are no customers that are lost or dropped. So if none lost or dropped. So it doesn't matter what the arrival process is. It doesn't matter how bursty, how non-bursty. So long as it has a well-defined arrival rate, lambda, then we can make this calculation. So you can go to any queue, and we'll look at some examples in a moment. And you can calculate the average number in the queue as a function of the arrival rate and the average delay. Or of course, if you know L and lambda, then you can figure out the average delay that's going to be seen by a customer through this queue. Now, L is the average number that are in the queue plus currently being serviced, so long as D is the average delay of customers that arrive until they've completed service. Turns out this result also holds if we say L is the average the average number of customers in just the queue but not yet entering service, so long as D also equals the average delay through the queue prior to entering service. So both of those are true. We're going to be using this result quite a lot throughout the quarter. Having told you about those three properties of queues, something I need to tell you before we get on to the fourth property, and that is the Poisson process. You're going to hear a lot about the Poisson process whenever you study queues or any complicated system that we model probabilistically. Okay, now first of all, I'm going to tell you what the Poisson process is, and I'm going to tell you why it's interesting and some caveats about using it. So the Poisson process is an arrival process in our case, and an arrival process we say is Poisson if, and in fact, and only if, the probability of there being k arrivals in an interval of t seconds is given by this expression here. Kind of a hairy expression, but the important thing is that that we can express this as the expected number of arrivals within an interval t is simply lambda t, where lambda is the arrival rate. Also, successive inter-arrival times are independent. What this means is that once we've picked one arrival from this expression here, this will lead to an arrival event happening, then the next arrival is independent of the first one. And in fact, if we take a sliding window and move that over the arrival process, within any period, the inter-arrival times within one period are independent of the next. That means that there's no burstiness or coupling of one arrival to another. Okay, that's what the Poisson process is. If you pick up any book on probability, then you can find a more detailed description if that's something that's new to you. So why the Poisson process? Why are we interested in the Poisson process? Well, the Poisson process happens to model an aggregation of many independent random events very well. For example, it's used in models of new phone calls arriving to a switch. So when we have a telephone switch and we say we want to model the arrival of a new phone call that is being placed through the day, then a Poisson process is a very good model of this. Or the decay of many independent nuclear particles, where we have a huge number of particles all operating independently of each other. They will decay at certain times. That decay as an aggregation of many random events tends to a Poisson process as we have a large number of particles. And you may also be familiar with shot noise in an electrical circuit, which is also modeled as a Poisson process. The final thing, despite the complexity of the equation on the previous slide, it actually makes the math very easy. And this is a big reason that it gets used very widely as well. At this point, I should give you some warnings. Network traffic is very bursty. There's nothing independent about one packet arrival after another. As we will see later, packets tend very frequently to arrive in bursts, and many things in the network help actually to keep them that way and make them very bursty. So packet arrivals are not, and I can't overemphasize this, they are not Poisson. There's been some classic papers, research papers that have shown this. However, it does model quite well the arrival of new flows, of new communications. For example, the inter-arrival times of web requests or sending emails. For any one individual, they may be somewhat Poisson, but when you take the aggregation of many users putting their network traffic into the network, that is actually modeled quite well by a Poisson process. And sometimes we can use some of the results that apply to queues with Poisson arrivals to give us an intuition, an understanding of maybe what's happening even at the packet level. But we must do that very, very carefully. Let's look at a very common example of where we use the Poisson process. This is something called the MM1 queue. The MM1 queue is about the simplest type of queue that is commonly analyzed. The notation is that the M stands for a Markovian arrival process, which in our case is Poisson, Markovian service process, which is exponential in our case, which means that the time that it takes to service a packet is exponentially distributed, and each one has a service time independent of all of the others, and that there is one server, in other words, that there's one outgoing line servicing this queue. This is very widely used because it assumes a nice simple Poisson arrival with independent arrivals from one packet to the next. But it's also used because the math is nice and simple and the result is very intuitive. So if we were to analyze this, and we can analyze it using continuous time Markov chains, we will discover that the average delay of a packet going through this queue is given by the simple expression 1 over mu minus lambda. What this tells us is that it's a 1 over the difference between the service rate and the arrival rate. So as the load increases and the load gets closer and closer to the service rate, then this number will grow very rapidly. And if we plot this on a graph, so as a function of lambda over mu, so that's lambda over mu, as we get closer and closer to 1, in other words, where they're equal, the average delay of a packet through this queue will increase very, very steeply. And this is the case for almost any queuing system, not just the MM1 queue. The reason that we use the MM1 queue sometimes as a placeholder for a more complicated system is only that the math is simpler and this expression is simple. But you see a very similar shape for almost any queuing system. We can use Little's result to figure out what the average queue occupancy is, and we know that L equals lambda times D, which in this case is simply going to be lambda over mu divided by 1 minus lambda over mu. The reason for writing it in terms of lambda over mu is simply that lambda over mu represents the intensity, just as I sketched on the graph here. As lambda approaches mu, lambda over mu approaches 1, and the denominator turns to 0, and the queue occupancy and the average delay will blow up and tend towards infinity. So the MM1 queue provides us a good intuition. Don't ever assume that this is the actual representative measure of the queue occupancy or the average delay, but it can often help to give it an intuitive sense of what's going on in a network. So in summary, the main queue properties I want you to take away from this video are that burstiness tends to increase delay. So bursty arrivals tend to make queuing delays longer. Little's result gives us a nice relationship between the average occupancy of a queue, L, lambda the arrival rate, and D, the average delay of a customer through that queue. While packet arrivals are not Poisson, some events are, such as web requests and new flow arrivals. And Poisson process also forms the basis of the MM1 queue, which is a simple queuing model that often can give us some intuition about the delay properties of a network. That's the end of this video.